Let's take a look at some of the evaluation parameters used by IBM Watson. So let's start with the confusion matrix. So this is basically a way to categorize the combination of predicted and actual values. So what it means is, now given the actual value, how did the algorithm perform in predicting them? So for example, the actual value was 1. If the algorithm thought it was 1, then it is a hit. But if the algorithm failed to think it was 1 and it thought it was 0, then that means the algorithm missed it. Now, if the actual value is 0 and the algorithm thought that it is 1, that is right about here, then it is a wrong hit. And if the actual value is 0 and the predicted value was 0, then it is a correct miss. That means the actual value is 0 and the algorithm also thought it was a 0. So I've given it some familiar names to make this easy to understand. Hope it works. So accuracy is basically the correct prediction divided by all the predictions. So this is not the best parameter to assess all types of different data and distributions of data. So let's look at some more of these parameters. Next is precision. This is basically the hit, which is the correct hit, divided by hit plus the wrong hit. So this measures the capability of the algorithm to guess the answer to be correct, given that the answer is correct. So keep in mind that this precision should be as close as possible to 1. Recall is hit by hit plus miss. So this basically measures the algorithm's capability to look throughout the dataset and find us the answers. So value closer to 1 also means high recall. Now you need to be able to strike a balance between precision and recall. After a certain point, which is break even, then they start going in opposite directions. So to understand these two parameters better and to make it easy to make a judgment call, there's something called the F-score, and this F-score is the harmonic distribution of the precision and recall. So if you just look at the F-score, you should be good to go. So an F-score closer to 1 is the better score. Let's look at some more parameters. Then we have the true positive rate, which is the same as precision. We also have the false positive rate, which is basically miss divided by miss plus correct miss. So if you actually plot the PR curve, so precision by recall, so as you can see that here, for example, if I take this spot here, so the recall is 0.9 and precision is 0.7, right? Now if I take this point, so for example, let's say here, so recall is 0.95, precision is 0.3. So after this point, they kind of reverse in their behavior. So before that, it's a different behavior. For example, if I draw a line here, goes all the way 0.7, and this is almost 0.99. So you want to take a relationship where the precision is balanced with recall. And there could be certain cases when you want the precision to be higher depending on the use case, and you can compromise on the recall. And there are some cases when you want the recall to be higher, when you can compromise on the precision. So for example, precision could be finding the cancer patients among many patients who come to the hospital, because you cannot make a mistake in missing out the patients who have cancer. And recall could be finding documents in a large set of documents. On the right hand side, you have the ROC curves. ROC stands for radio operator characteristics. So as you can see here, you have the false positive rate and true positive rate. And we want to be on this yellow curve, which is the excellent curve. So here the behavior is almost inversely proportional. So for example, 0.1 false positive rate, so go all the way up. Now here you can see 0.9 true positive rate. So the area scores are between 0 and 1. So it tells you the sensitivity and tells you the performance of the algorithm. So your scores need to be as close as possible to 1, 1 being the best score. Let's take a look at some more characteristics. And we have the mean squared error. So this is very simple. So we have the actual, and then we have the predicted, which the algorithm thinks. You basically take a mean and you square the difference of the actual versus predicted. So that becomes your mean squared error. So n is your number of samples. This is just summation of 1 to n. And then you have your actual, you have your predicted, and you're just squaring the difference of these two. Root mean squared is, as the name says, root of mean squared error. Mean actual error is basically mean squared error without being squared. So just imagine this formula without the square. So these error measures give you an understanding of how far your predicted values are from the actual values.